In a previous video we calculated this double integral by first of all calculating this integral here, integrating with respect to y, and then integrating the result with respect to x. So that means that we considered slices of the region that we were integrating over in the vertical direction. Now in this video we will consider cross sections of the region that we are integrating over in the horizontal direction. Any point on this vertical line has x value 1. What about a point on the curve? Well, we can make x the subject of this equation. X equals the square root of y, and we're actually taking the positive square root of y here because we're dealing with a curve that's above the x-axis. So we are interested in the area of the cross section of the volume under the graph of 2x sine y, but along this line here. Okay, again I cannot show this, the z-axis is coming out of the screen. Anyway, you can see that we have to integrate with respect to x, so we're integrating from x equals root y to x equals 1. So I've changed the order of integration here. We are integrating with respect to x firstly, whereas before we were integrating with respect to y. So we are treating y as a constant, so sine y is a constant. If we integrate 2x, we get x squared. We apply our limits. We set x equal to 1, we get 1 squared sine y, that's just sine y. Then we have a minus sign. We plug root y in for x. Root y squared is just y. We can factorize sine y out of this to get 1 minus y times sine of y. So the next stage is to consider slices of width dy. You can see that the width has to be equal to dy. Vertical distance here, the width of each slice, and we have to sum all those slices from, well, the lowest value of y, which is 0, to the highest value of y, which is 1. So you've got to imagine a load of horizontal slices running from y equals 0 to y equals 1, and that's exactly what we are doing with this integral here. So we can see our limits are from y equals 0 to y equals 1. So you can see that when we switch the order of integration, we get different limits. We can't just use the same limits. Now with this integral we have to use integration by parts. 1 minus y is an algebraic term or function. Sine y is trigonometric. So if we use our rule LIATE, we see that a takes precedence over t. Okay, a comes before t in this rule, so we set u equal to the algebraic term. So du is equal to minus dy, and dv then is differential, which is sine y dy. So to get v, we integrate sine y with respect to y, and the integral of the sine function is minus cos. So we multiply u by v, so 1 minus y times minus cos y gives us this here, and we apply our limits, y equals 0 to y equals 1. Then we've minus the integral of v times du, so that's minus cos y times minus dy. Okay, so we've minus the integral of minus cos y by minus dy, which gives us this here. If we plug 1 in for y, you can see that we get 0. If we plug 0 in for y, we get minus bracket 1 minus 0 times the cos of 0. Well, the cos of 0 is 1. Now the integral of the cos function is sine. All of this thing works out to plus 1, and here we get minus sine 1 minus sine 0, sine of 0, 0. So you see that we get the same answer as before. We get 1 minus sine of 1. Now, in this example here, if we try to evaluate the inner integral first, we will find that we cannot do it. There is no algebraic approach to integrating e to the power of y squared with respect to y. Let's consider the region that we are integrating e to the power of y squared over. We are integrating from x equals 0 to x equals 1, and from y equals x to y equals 1. Y equals x is a straight line passing through the origin. It's got a slope of 1. Okay, it's got the form y equals 1x plus 0, so the intercept is 0. The y-intercept is 0, the slope is plus 1. It's actually a line that makes an angle of 45 degrees with the positive x-axis. So for a general point x between 0 and 1, the y value of this point is equal to x, but the y value of this point is plus 1. The y value is 1 for points anywhere on this horizontal line. So if we could evaluate this inner integral here, we would be getting the cross-sectional area under the surface e to the y squared in this direction, in this vertical direction, from this point to this point here. Of course, we can't get that cross-sectional area algebraically. We can do it numerically to arbitrary accuracy. Okay, but we need to be able to solve these integrals algebraically. Of course, we know what the next step is. If we could do this, if we could get this cross-sectional area, we would multiply by the width dx of a slice, and of course we'd sum all those slices from x equals 0 to x equals 1, so we'd be considering vertical slices of width dx running from 0 to 1. Alright, so we can't do this algebraically. However, we can calculate this double integral by considering slices in the horizontal direction instead. So remember, we're getting the volume between this triangular region and the surface e to the power of y squared. So it doesn't matter how we do it, whether we consider vertical slices or horizontal slices when calculating that volume, the result will be the same. So let's look at the endpoints of horizontal slice of our triangular region. Well, the x value of the left point is going to be 0 because it's a point on the y-axis. The rightmost point is a point on the line y equals x. We want the cross-sectional area under the surface along this horizontal line. So we are running from x equals 0 to, well, x equals y actually. We are integrating with respect to x. So we need to evaluate this integral here. Now this is a straightforward integral. So we're integrating e to the power of y squared with respect to x. So y is a constant, hence e to the y squared is treated as a constant. So we just multiply e to the y squared by x. And our limits are from x equals 0 to x equals y. So we need to get a function of y alone here, because then we have to integrate the result with respect to y. So we know that our limits have to involve y. So, you know, whatever these quantities are, they must be involving y only, or constants, like, well, 0 is a constant, 0 or some function of y. So that we end up getting an expression in y for this inner integral. Okay, so we plug y in for x, so we get y e to the y squared. Then we have a minus sign and we plug 0 in for x. Well, that's just going to give us 0. So the inner integral is y e to the y squared. So let's again look at the geometrical interpretation of what's going on. We have the cross-sectional area under the surface e to the y squared in the horizontal direction for any line, horizontal line, okay, running from x equals 0 to x equals y, and you can see obviously y is varying, so it depends on what y is. So for different values of y we will have different cross-sectional areas. So the cross-sectional area is a function of y alone. We know that to get the volume we have to consider slices of width dy in this case, because we're have to sum all these slices. So we have to integrate y e to the y squared with respect to y from this value here up to this value here, from y equals 0 to y equals 1. So we now know the limits of this outer integral must run from y equals 0 to y equals 1. We get that from the picture. So we're considering all such slices from 0 to 1. Each slice has width dy. Now we don't have to use integration by parts because we can see that y is just the derivative of y squared. So if we let u equal y squared, we can easily solve this integral. We see that du is 2y dy. So it follows that dy is just du divided by 2y, so the y's cancel and we get a straightforward integral. Now let's check out the limits. So when y is 0, we see that u is 0, so the lower limit here is 0, and when y is 1 we see that u is equal to 1 squared. Well, that's 1, so when y is 1 u is also 1. So we have a half times the integral of e to the u with respect to u. The integral of e to the u is just e to the u. We plug in our limits, we get a half into e minus 1.